So when Pierre-Antoine said it was crazy to cram an hour-long talk into a lightning talk, I took that as a challenge. Because I gave an hour-long presentation at CppCon last year that was a complete and thorough introduction to C++ templates. I thought you might like to see that talk here. But I only have 5 minutes, so I'll have to go through this very fast. Pay attention. The basics. The template keyword followed by template parameters. Lots of things can be templates. Define your templates in header files. An example of a class template. The keyword template, template parameters, use template parameters as types. You can use the keyword type name instead of class. And type alias template example, variable template example. How to define a template parameter. A type template parameter represents a type. A non-type template parameter represents a compile time value. A template parameter represents a template. Template parameter names are optional. Template parameters can have default values. Template parameters can be variadic. Non-type template parameter example, std array. It has a type template parameter. It has a non-type template parameter of type size t. Class templates can have member functions. Define them in the class because defining them outside the class is complicated. To use a template, it's a template name followed by template arguments. Example, where arguments are all types. Sometimes template arguments can be left out. Substitution versus instantiation. Substitution checks the correctness of template arguments. Instantiation checks the full definition. For classes, substitution results in an incomplete type. For functions, substitution happens during overload resolution. For classes, instantiation results in a complete type. Example of a class template. Instantiate it with int and data. Behaves as if this were in the source code. Instantiate it with array of int and data. Equivalent to this, the data member is fine, the parameter is fine, but the member function returns an array. That's a compilation error. Instantiation of a function template gives a complete function definition. Example of a function template instantiated with double. Substitution failure is not an error. Instantiation failure is an error. Using class templates. Each instantiation is a separate type. Different instantiations of the same template can't be implicitly converted, even if the arguments are closely related types. Std array, again, is an example of a non-type template parameter. It can be instantiated with a type and a compile time value. Instantiating with 2 types is an error. Instantiating with 2 constants is an error. Class template C has a template parameter. If we instantiate C with a type, the compiler complains. Instantiating C with template A is fine. Instantiating C with B won't work. B is the wrong kind of template parameter. The compiler complains. Using function templates. Don't specify template arguments. Let the compiler deduce them. For example, to transform reduce has 5 template parameters, but none of them are specified when calling it. They are all deduced. Constraints. Use constraints to specify the requirements on template arguments. This function only makes sense for integral types. How can we specify that? Enable if on the return type, or enable if on a dummy template parameter, or a requires clause that checks a type trait or a concept in the template parameter, or a trailing requires clause that checks a type trait or a concept, or a C++20 constrained auto function parameter. This is a template, despite the lack of the template keyword. Writing class templates. Keep it simple. Document the expectations on template parameters, with constraints if possible. Specialization is defining a class that will be used instead of an instantiation. We want safe size of, which returns 0 for types where the size of operator is an error. This by itself isn't enough. A specialization for type void, an empty parameter list, specify the instantiation that this is a specialization for, return 0 instead of using the size of operator. Works for void, but still fails for other incomplete types. We need partial specializations to fix that. Add 2 partial specializations. The first matches unbounded arrays, the second matches function types. This handles most cases, but not all. This is not a good design, so flip things around. The main template handles all the problematic cases. The partial specialization handles all the normal cases. This safe size of works correctly, but it's better written as a variable template than a class template. Class and variable templates can be specialized. Type alias templates and concepts cannot. Function templates are complicated. The type name keyword must precede the qualified name of a type that depends on a template parameter. Example of that on the previous slide. Because C++ declaration syntax is a mess. This can be parsed 3 different ways, as an expression statement, as a variable definition, as a function declaration. If a name depends on a template parameter, the compiler doesn't know how to parse this. Humans know that value type is the type name, so this is a variable definition, but the compiler assumes value type is not a type. The compiler tells us how to fix this. If we do that, it's all good. Writing function templates. Make all template parameters deducible, except when its only use is in the return type. The compiler can't deduce the parent type of a function parameter. This one is pretty obvious. Why not? This one is more subtle, but it's still not deducible. Avoid complicated overload sets. Stood vector is an example of what not to do. Avoid function templates that accept everything. This is really bad. It will match more calls than you want it to. Rules for function template specialization are complicated, so ignore them. Don't specialize function templates. Use overloading instead of specialization. Non-template overloads instead of full specialization. Template overloads instead of partial specialization. Wait, what's that? Oh, you're in French. And now you are all template experts.